Awesome. Thanks so much for the invitation and for the kind introduction. So yes, I'm going to talk about a couple of new use cases for generative AI and language models in particular in the context of data management. And we have already heard a little bit about language models in the previous talk, and some of you might also have come across headlines like the ones that you see here, which generally discuss recent advances in the domain of generative AI and language processing. And those advances are filled primarily by two ideas. First of all, we had a novel neural network architecture, the so-called transformer, which makes it significantly easier than prior methods to create very large neural network models with up to hundreds of billions of parameters. And then we had some advances in how to train those large models using transfer learning ideas, which essentially means that we train or with a large amount of unlabeled training data, and then try to generalize from that in order to solve a variety of tasks. For instance, one common pre-training objective that is used on those transformer models is to simply predict the next word in a sentence. And for that, as you can imagine, we can just use training data that we find on the web. And it turns out that those models that have been pre-trained with those tasks, they can generalize from the specific task and solve other tasks as well that are described to them in natural language alone. So here in this little video, for instance, I'm showing you how I use ChatGPT, which is one of the most recently released language models. And I'm asking it to do a task which certainly is not part of any standard NLP benchmark. I'm asking it to write a little poem about this seminar over here. Right, so let's see what it is doing here. Okay, giving it a little bit of context. I want to use that in my talk, so let's see what it does. And as you see here, it replies in a colloquial manner, and now it is writing something that is actually, that probably qualifies as a poem. It rhymes, and in terms of content, it matches the instructions that I have given it. It's interesting, you see that it has apparently extracted some common sense knowledge from the pre-training data corpus. For instance, it automatically matches my input request to cities in the Netherlands, which I haven't specified as part of the input. And I mean, in terms of the length, this is something which would have been difficult to generate just a couple of years ago. And most importantly, I'm only specifying this task in natural language. I don't have to specify any training samples or provide a large training corpora with poems about different database seminars, but it can spontaneously solve this task. So this goes to show you that there has been a lot of interesting progress in the domain of language processing, including natural language, as well as formal languages like SQL or various programming languages. And I think that makes it interesting to think about use cases in the domain of data management. And in the following, I'm going to present a couple of those use cases. A first use case is the good old problem of database parameter tuning, because those database systems like Postgres, they tend to have hundreds of tuning parameters, allowing you to configure every aspect of data processing. Here on the left-hand side, you see a few sample parameters, and that creates the problem of finding optimal settings for those parameters in order to optimize a specific performance metric like throughput or latency for a specific workload. And now it might, first of all, be surprising how language processing can help us for this rather traditional database optimization problem. But remember the good old saying, when all else fails, read the instructions. And if you would be tuning a database management system, I assume that you would first of all have a good look into the database manual. And probably not only that, but you would probably Google in order to find web sources with useful hints about database performance tuning. And you would find them. For instance, here you see a couple of useful sources of tuning hints for the Postgres database management system, including, for instance, discussions on Stack Overflow, blog entries about database performance, and of course, the online manual. And in all of those text sources, you find some very useful hints about how to set specific parameters in specific scenarios. So now the DB-BERT system is the first automated tuning tool which automatically extracts such tuning hints from text documents in order to get a better starting point for automated database tuning. Now, this is the high-level overview of how that system works. The input to the system is, first of all, a workload that you want to tune, as well as a performance metric that you want to optimize, like latency or throughput. And then, and this is specific to this system, users can also specify a couple of natural language keywords which somehow relate to the tuning context. That could be, for instance, a description of tuning goals of the tuning platform or of the database or workload that you're tuning for. Now, DB-BERT is particular in that it uses those keywords and queries the web using the Google API automatically in order to retrieve relevant text documents that might contain helpful hints for tuning in this scenario. Of course, we cannot trust those web hints because you find a lot of things on the web. This is why DB-BERT complements those text hints by executing live trial runs with the specific workload that we are tuning for in order to validate which of those hints that it finds on the web are actually reliable. After user-specified timeout, the system returns the best configuration that it has found so far, which optimizes the user-specified performance metric on the user-specified workload. Internally, the system executes two phases. There's a pre-processing phase, which works with the input text documents, and then there's an iterative learning phase, which it validates and adapts those hints. I'm going to discuss both of those phases in a little bit more detail in the following. Now, during pre-processing, the goal is to extract tuning hints from text documents to translate those hints into a formal representation that enables the system to automatically apply them, and also to fix an ordering between those hints in which they are validated in the following phases. Now, this is the high-level overview of the text processing pipeline that the system uses in the pre-processing stage. The input are text passages, and for those text passages, the system first links them to relevant configuration parameters of the database management system, then tries to extract the formulas that represent recommended settings for those parameters and may depend on system properties such as the total amount of RAM that is available. Finally, resolves those formulas into concrete values, and the result of that are hints which map specific parameters to specific values. Now let's make things a little bit more concrete by an example. So here you see three text passages that provide tuning hints for the Postgres database management system. So the first step would be to detect the parameters that those text passages refer to. And you see that for the left two text passages, that is actually quite easy because they explicitly mention the name of the parameter that they are referring to. Whereas for the last passage, it doesn't actually explicitly mention the parameter name, but it rather describes the desired effect. So it would be up to DB-BERT to link that to the parameter that is relevant. Now, given those parameters, we want to extract recommendations for those parameters. And here we're extracting text snippets that recommend specific settings for those parameters. Now, as you see, those text snippets are still in natural language. So in order to make it automatically usable, we want to translate them into formulas that express a recommended setting for the parameter. Now we have done that, but you see that those formulas still contain placeholders in order to represent, for instance, system properties, such as the total amount of RAM that is available. And when tuning for a concrete server, then we want to replace those placeholders by the specific values that apply to this machine, and then resolve those formulas into concrete value recommendation, which I'm doing here. And the result of that are those tuning hints which link a specific parameter name marked in red to a specific value. Now, the final step in preprocessing is to order those different hints based on the parameters that they are referring to, using the rule of thumb that parameters which are frequently mentioned on the web, they tend to be more relevant for performance, and corresponding hints should be tried out first. And with that, the preprocessing stage, which is executed once per tuning session, is finished. Now, as discussed, preprocessing extracts tuning hints from the web, but we cannot really trust those tuning hints. So in the learning phase, we are figuring out which of those hints are actually applicable and how we should adapt them in order to work best for our concrete tuning scenario. So we might want to adapt the recommended values in order to better match our current scenario. We might have conflicting hints about how to set the same parameter from different sources. Then we have to decide how to prioritize between different hints. And then, of course, we have to select a subset possibly of those hints in order to aggregate them into a configuration that we actually want to try out and evaluate by a live trial run. So that is the goal of the learning phase. Now, how it works on a high level is that the system selects specific configurations to try out and then evaluates them using a user-specified workload, and it measures the performance that we are getting with specific parameter settings. And that creates the problem to decide which configuration to try out next. And here we have a choice. We can, for instance, choose to evaluate next configurations that are somewhat similar to configurations that we have tried out in previous iterations. That is called exploitation. But if we only do this, then we will probably get stuck in local optima. Every once in a while, we also want to explore configurations that are very different from all the configurations that we have seen before. Now we can imagine that there's often a tension between those two motivations, trying out something that has proven to work well and trying out something completely new. And that tension is often called the exploration-exploitation dilemma. And the most principled way of resolving this tension is by using a reinforcement learning framework. Now, in reinforcement learning, we generally have an agent which interacts with an environment, and the agent can influence the environment by applying so-called actions. From the environment, the agent obtains information in the form of so-called observations that it can use in order to decide which action is most appropriate next. Also, the environment returns reward values for the actions, and the goal of the agent is to maximize the accumulated reward that it collects. But initially, the agent does not know how the environment works, so it has to figure that out by a principled version of trial and error. Now, mapping this scenario to the one that we are facing here, the agent, that would be, of course, the DB-BERT system, and the environment would be characterized by workload and by system properties. Actions would be associated with adapting values recommended in those hints, deciding on how to prioritize between different hints, and deciding how to aggregate different hints into a common configuration. Observations are associated with the hint text, and the rewards are given, first of all, for trying out parameter values that are accepted by the database management system, then also for trying out parameter values that lead to performance improvements compared to the default configurations. This is what the agent tries to optimize. Let's continue with the example that we have seen before. So after pre-processing, we end up with this matrix over here. Now, the next step would be to decide how to adapt the recommended values. And here the system might try to multiply the recommended values by small factors, which could be larger than 1 or smaller than 1. The next decision would be to decide on how to prioritize between conflicting hints about the same parameter. And that means that the system is assigning weight values to the different hints. And then if the weight is higher, the system will prioritize these hints if it conflicts with other hints. So choosing those weights would be another decision. And then finally aggregating all of those hints into configurations that can be tried out and evaluated via trial runs. So here we have a whole sequence of decisions that the system is making. And just as a little reminder, the upper part of this matrix is determined once per tuning session during pre-processing. The lower part of this matrix, those are decisions that are made iteratively and in order to learn optimal settings for those decisions, because they may depend on the specific workload in the specific context that we are tuning for. Now, let's make things a little bit more concrete. So here I'm going to show you a little demo of the user interface of DB-BERT. So you can also find the code on the GitHub repository. I have the link on the right-hand side. And the first thing that I want to do here is to select a text source that will be used in order to extract tuning hints. Here, I have already automatically extracted tuning hints that you get when issuing the Google query Postgres performance tuning. The system automatically downloads the first 100 web documents that you get for this Google query. And now I'm selecting the downloaded websites as a text source for tuning. So that is Postgres 100. Now, in addition to the text source, I also need to tell the system a little bit about the hardware properties of the platform that I'm tuning for. The reason is that we have those relative tuning hints, which contain placeholders for hardware properties such as the amount of RAM that is available or the number of CPU cores that I have on my target platform. In order to translate those relative hints into concrete recommendations, I need to tell DB-BERT a little bit about the target server that we are tuning for. And then, of course, DB-BERT performs live trial runs in order to learn how to adapt and how to prioritize between the hints that it extracts. And for that, it needs access to the target database that I am tuning for, which I'm providing here. And then finally, I can select a metric to tune for, either minimizing runtime or maximizing a throughput in the current system. And then I'm selecting queries that the system should tune for here. Those queries are actually queries taken from the TPCH benchmark. Now I can start the tuning session. Pre-processing takes perhaps half a minute, 1 minute, depending on the size of the input text and the GPU support on your tuning platform. And the result of that is, first of all, a table with extracted tuning hints. Here, for instance, you see a tuning hint about the shared buffers parameter in Postgres, which should be set to 25% of available RAM. So here, the system has automatically inferred, first of all, that this is a text passage, which is likely to contain a tuning hint. Then it has automatically linked the text passage to the parameter, which in this case is a little bit easier because the parameter is explicitly mentioned. And it has extracted the recommended value, which is relative. It's 25%. And it has extracted the resource that this recommendation refers to, which is the total amount of RAM available. So all of those decisions are correct. And now the system will try to adapt and to prioritize the extracted hints in the learning phase. And here you can see the decision that it makes for each of those tuning hints that it has extracted during preprocessing. So here, first of all, it decides to multiply the recommended value by factor 0.5. So it just tries out to go a little bit below the recommended value. It also assigns a weight to the tuning hint of 16, which is pretty high. So this hint would get prioritized compared to other hints in the extracted set. And here, first of all, when trying out this hint on the database management system, it turns out that the database management system does not throw an error, but it accepts the new setting, which is already a first success, because some of those tuning hints that you find on the web, they might recommend values that are outside of the range of admissible values. Here, the system accepts the extracted value, which means that you already get an assignment reward of a moderate 10 points. The other column here, P reward, stands for performance reward, and those are reward components that are assigned for improving the performance compared to the default configuration. Now, actually evaluating a configuration is expensive because you have to actually run all of those queries in the input workload. So the DB-BERT system doesn't do this after each tuning hint, but it rather waits until it has accumulated a couple of tuning hints, and then it evaluates the combination of tuning hints. Now, this is what is happening here, and you see that the system, I quickly go back to where I was here. So here you see a reward of 600, which means that the system managed to improve the performance compared to the default settings. The table above gives you more in-depth information about all the trial runs that DB-BERT has executed with the default configuration. Here we're getting a runtime of 24 seconds. Now, after a couple of minutes of tuning time, the system already finds configurations that are significantly better and save about 6 seconds compared to the initial configuration. So here, by extracting those tuning hints from text documents, the DB-BERT was able to relatively quickly find configurations that work significantly better than the default settings. Now here I'm showing you a little extract from the experimental evaluation. Here on the x-axis, you have tuning time. On the y-axis, you have the execution time for the best configuration when executing TPCH on MySQL. And here I'm comparing DB-BERT to multiple baselines. Now, the input text documents that DB-BERT is using here are the ones that you get when running the Google query MySQL performance tuning and taking the first 100 websites that you find. And here I'm comparing to DDPG++ in multiple configurations, which is a baseline that only uses reinforcement learning in order to try out different configurations for MySQL. I'm also comparing to a baseline that only uses natural language processing in order to extract hints from text documents, but doesn't actually try out those hints in order to validate which of them actually make sense. And then there's DB-BERT, which essentially combines those two sources of information. It uses information extracted from text, but it also uses information gained via live trial runs. And as you see here, that enables it to reduce the execution time significantly faster compared to the baselines. Now, this is a TPCH, where we want to minimize runtime. Here you see some results for TPCC, where the goal would be to maximize throughput typically. And again, you have a similar picture. DB-BERT is able to find better configurations than the baselines relatively quickly. And this is just a small extract from the experiments. You find more of them in the paper with different database management systems, different input text sources, and for different benchmarks. But the high-level outcome is that by unlocking this additional source of information, which is text data, DB-BERT is able to find good configurations faster than baselines. So now what you see here is the evolution of language models over the past couple of years measured by the number of trainable parameters. So the y-axis, that is the number of parameters, it's measured in the billions. And you see here that it is a logarithmic axis. So we're actually talking about a pretty significant evolution here. On the x-axis, you have time covering just the past couple of years, basically. And it turns out that DB-BERT actually already works quite well when using language models with parameter counts in the hundreds of millions of parameters, which used to be a lot, but nowadays we actually have significantly larger models, often with parameter sizes in the hundreds of billions of parameters. And the question is, what else can we do when using those much more powerful models that we have nowadays? And one way of exploiting those much larger models is what I'm going to discuss here for a system called CodexDB. As opposed to tuning an existing database management system here, the goal is closer to trying to write a specialized database analysis system from scratch, basically. Imagine the following situation. So imagine you want to process an SQL query. You could, of course, use an existing database management system like Postgres, but let's say that you have some particular constraints about how this query should be executed. Maybe you want to specialize to a specific platform or data set. Maybe you want to generate highly custom output while processing the query, or you want to use specific libraries for processing the query. For whatever reason, you don't want to use Postgres, And what you have to do essentially in order to achieve the highest degree of customizability would be to, for instance, if you have developers, to essentially give that SQL query to one of them, describe probably in natural language how you want to customize query processing. And then if you're lucky, after a couple of hours, you get a customized code for processing this query, which ideally implements the natural language instructions that you have given. Now, the goal of CodexDB is to essentially automate this process and create a system that essentially takes an SQL query as input, which should be processed on a collection of raw data files, could be, for instance, a collection of CSV data files, and you want to execute this query using code that complies with additional natural language instructions that you provide as part of the input. The output of the system is code in general purpose languages such as Python, which when executed process the query on the raw data while complying with your natural language instructions. Now, among the possible use cases are, for instance, the ones that you see here. For instance, you might want to do some rapid prototyping of different processing mechanisms for a given query workload in order to get some insights into the performance that you could be getting. Maybe you want to integrate a code into an existing code base, and so it should be consistent with the libraries and the data structures that are using within that code base. Maybe you want to generate custom logging output or process custom data formats. There's various use cases in which it helps you to be able to write customized code for your specific query. Now here you see a little demo of the interface behind CodexDB. What I have already done here before the video starts is selecting a data source, meaning collection of raw data files, and I have already entered an SQL query which relates to those data files. Now what I'm going to do in addition is to specify natural language instructions that describe desired properties of the code that the system generates in order to process the SQL query. Let's, for instance, start with something simple. Let's say I want to generate code that uses the CSV library in Python. Now I'm entering those natural language instructions, hit on generate code. And now the first thing that CodexDB is doing is to generate a so-called prompt, which essentially describes the data generation task to the neural network, a model which will take care of the actual code generation. And this prompt contains lots of useful information about the data and about the query that I want to process. I'm going to detail the mechanism for prompt generation a little bit later. And now here, after a couple of seconds, the model has processed this prompt and translated it into corresponding Python code, which you see here, and as requested, it is using the CSV library. Or for the same query, let's, for instance, say I want to use a different library. Let's say I want to use the pandas library, which is also a library for data processing. Again, the system generates a prompt, takes a couple of seconds because I'm currently using the most powerful version of the GPT-3 model. And after those couple of seconds here, the system again generates code which processes this query on raw data, and it complies with the natural language instructions as it uses the pandas library. And if you compare those two pieces of code for the same query, here in the pandas version, here in the CSV version, you see that it differs quite a little bit in terms of the length and in terms of the code structure. All right, so we're going to see more examples later, but this is just to give you a little impression for how the interface of the CodexDB system works. And that is only possible since relatively recently, this system currently uses the GPT-3 model in the background, and not the base version, but actually a specialized version for code generation that I'm currently beta testing. And as you have already seen in that little demo, the input is a natural language prompt, which describes the code generation task. The output is code implementing those instructions. So this model has been released in the first version in the second half of 21. In the meantime, there have been updates to the model. So the experiments that I'm going to show later use the latest version of this model. All right, so how can we use this model in order to generate a code that processes SQL queries? Let's not even talk about customization yet, that comes later, but we just want to generate code which processes an SQL query on raw data. All right, so the most straightforward way to use this model for generating code for processing SQL queries would be pretty much the architecture that you're seeing here. So the input should be some kind of database catalog, which simply describes the structure of the raw data, for instance, like the columns that you find in those CSV files. Now, the description of the raw data together with the SQL query could be put together into this prompt that will provide the input to the GPT-3 Codex model. And this is how the prompt could look like. So here I'm coloring different parts of the prompt based on their semantics. And you see here in yellow, for instance, we have some description of the database schema with basically the tables, which are represented simply by CSV files on disk, as well as the column headers that you find there. In green, you have information about the physical location of those files, and in red, you have the SQL query that should be processed on this raw data. And that is relatively subtle, but in blue, you have those three quotes, which are a subtle hint to a GPT-3 Codex about the target programming language that we want to generate code in. Those three quotes are essentially linked to Python. In principle, GPT-3 Codex is able to generate code for a variety of programming languages. Now, given this prompt, I can send this prompt to the GPT-3 Codex model. Hopefully, it will generate a suitable code. I can execute that code and then check whether the result generated by executing the code matches the query result that I am expecting. Now, I have evaluated this straightforward approach on a couple of benchmarks. For instance, the WikiSQL benchmark, which contains the relatively simple queries. Here I'm using DaVinci, which is the largest version of GPT-3 Codex in terms of the number of trainable parameters. So that is the most powerful one. Cushman is the second largest version of GPT-3 Codex. And now I'm essentially measuring, given 100 queries, for how many of them can the system generate a code that actually process those queries using the prompt structure that I have just introduced. It turns out this doesn't work. So for 0 out of 100 cases, the system is generating the code that processes the correct query result. So it seems that directly generating an entire piece of code in a general purpose programming language that processes an SQL query is perhaps a little bit too difficult. So what can we do? Fortunately, in databases, we have a lot of experience about how we can decompose complex queries into a sequence of simple processing steps by a process called query planning. So it might make sense to use similar ideas in this context over here, but there's a catch because query plans are typically expressed as a tree in a structured format, basically. Whereas GPT-3 Codex and other language models, they only process a textual input. And because of that, we have a specialized query planner here that produces a query plan, not represented as a tree, but rather represented as a natural language instructions using operator-specific templates in order to express a query plan in natural language. So this is how the expanded architecture looks like. The SQL query is first of all parsed, and then there's a planner which describes its query plans as text documents, works on the query, and produces such text. And this text forms one of the inputs during the prompt generation stage. This is how one of those expanded prompts look like. The only thing that has changed compared to the previous prompt is the part marked in red. In the previous version, there was simply an SQL query specification. Here, instead, we have a description of processing steps that has been automatically generated based on the SQL query. And this query plan is expressed in natural language. Now, using this type of prompt supported by a version of query planning, we can increase the precision to up to 22% of queries solved using the most powerful GPT-3 Codex version. So that's already much better. Of course, 22%, it's not yet great. We ideally want to do better than that, right? So this is a good step, but how can we make things even better? And one commonly used approach in this domain that also relates to topics discussed in the previous talk is to use few-shot learning. So often those models work much better if you provide them as part of the input prompt a couple of examples of successfully solved tasks of the same type that you wanted to solve. That's not always necessary, of course. It would basically mean, like in the input example, I would provide a sample poem before I'm asking the system to come up with a new poem. I haven't done that there. But here in this scenario, it might actually make sense to do that and show the system a couple of examples of code pieces that process SQL queries. Now, of course, I want to avoid having users write those code samples themselves. So instead of that, it's much better if the system can actually generate those code samples automatically in a pre-processing stage. And this is what the system is actually doing. So there's a pre-processing stage in which the system automatically generates code for a set of sample SQL queries, which don't have to refer to the same database than the one used at runtime, for instance. And for those sample queries, it keeps regenerating a code with a certain degree of randomization, and then it automatically verifies the generated code by processing it in order to generate a query result, then comparing this query result to the output that is generated by the same query by a reference system. And for those queries where it succeeds at generating code which passes all of those checks, the system adds them into a library, and then at runtime, it randomly selects samples from that library in order to integrate them as part of the prompts. Let's see whether that improves the precision in any way. And as it turns out, it definitely does. So here you see we are at about 80% when using the most powerful version. Here it's only using 2 randomly selected samples in the prompt that originate from this pre-processing stage. Now, finally, we have discussed about how to generate a code for processing SQL queries. But the reason why we were doing all of this is that we want to customize the generated code using natural language instructions. So that is the last missing piece here. How do we deal with those natural language instructions? Fortunately, it turns out that this part is pretty easy because our entire prompt is already kept in natural language. That means if users want to add more natural language in order to constrain the way the code is generated, we can simply take the user instructions and insert them as part of this prompt over here. For instance, here marked with a black background, you see the user instruction use pandas library, which I have used in the original example. You can just put this here as part of the prompt. Now, here you see a little example, just giving you a better look at how the code differs. If we provide those instructions on the left-hand side, you see a code for a query generated without further customization instructions. Right-hand side, you see the code generated when issuing the instructions use pandas library. And as you see here, it has a different length and has quite a bit of a different structure. So by natural language instruction, you can actually change the structure of the code quite a bit. Here you see experimental results where on the x-axis you have different instructions, slightly shortened, about how the system should process queries. The first 3 instructions that you see here, they instruct the system to generate code that uses a specific libraries. Could be important, for instance, if you want to benchmark different libraries, or if you want to integrate a generated code as part of a larger code base that uses a specific library. On the right-hand side, you see instructions about generating custom output while processing those queries, for instance, printing out intermediate result samples, which can be helpful for query debugging. Now here in blue and green, you see results for 2 different benchmarks, the WikiSQL benchmark and the so-called Spider benchmark, which is significantly more complex and contains queries with joins, with subqueries, grouping, aggregation, and so on. On the y-axis, again, you have the success ratio. And you see here that when processing those queries, the success ratio actually differs quite a little bit depending on which instructions we are providing, but in most cases, for the majority of queries, the system is able to produce a code that is correct. For the other cases, actually, even though that is difficult to measure, but in my experience, the code it generates can be fixed by relatively small additions. So this is the success ratio, but perhaps even more importantly, we want to quantify whether the generated code actually implements those natural language instructions. And here it turns out that the news are actually really good. For instance, when checking the generated programs in terms of the libraries that they are using, it turns out that a high percentage of those programs, essentially 100% of those programs, does indeed import the requested libraries, whereas without further instructions, only a small percentage of programs import any of the libraries by chance. And if that happens, it's typically the pandas library. Now, when checking programs for whether or not they generate the desired output, it's a little bit harder to find what the ground truth is, because some of those instructions, such as print progress updates, they leave quite a little bit to interpretation. But at least we can divide output into different categories based on, for instance, whether it prints out variables or whether it prints out constant strings. And there it turns out that nearly all of the generated programs, they do indeed generate the right category of output, whereas without further instructions, only a very small percentage of programs generates any output at all. That was a little extract, and in the paper you find more prompt variants, you find more analysis of generated code, and more benchmarking. So in conclusion, those were a couple of novel use cases for language models in the context of data management. Here I've discussed about a DB-BERT, which mines tuning hints from text documents for automated database tuning. CodexDB goes essentially one step further and generates a specialized query-specific code that can be customized by natural language instructions. There's also another system which that was recently published at DB, which essentially mines data for patterns that are described in natural language that I won't have time to discuss here anymore. You find code for those systems on my GitHub repository. And if you are generally interested to learn more about language models and the use cases in data management, I recommend you to check out my DB tutorial, which is also available online. So thanks so much for the invitation. And now I look forward to your questions.